Hello, good evening, everyone. So, welcome to the week 10th of this tutorial session on this course, Digital Signal Processing and its application. So, just a minute. Yes, so this course is, so today we will discuss the questions based on the topics covered in the week 10th of this course. And this video is also recorded and it will be uploaded on YouTube so that the student who cannot join now can watch it later. So today we are going to study about the digital filters and we will see how to represent the digital basic structure of digital filter like direct form, realization of IIR and FIR filters. And then we will also solve questions based on this. So the overall structure we will see like the first the input signal xt is given to the analog to digital converter. So once xt when the ADC converts xt, so we will get xn here because it converts analog to digital. Then we will pass this to digital filter. So we will get our y of n. Then again, for reconstruct back the signal, what we will do, we will again pass this to the digital to analog converter because now we have a digital signal. Again, we will get y of t after passing to the reconstruction filter. Finally, we will pass. So this is system for filtering a continuous time signal built around a digital filter. Okay. So there are two kinds of system. That is the finite impulse response system. Or you can also say that finite resonant impulse response digital filter. So the first one is FIR, that is finite impulse response digital filter. So in this there is a linear constant coefficient difference equation of a non-recursive nature. So this finite impulse response is non-recursive nature. So it has a finite values things. And the transfer function of FIR digital filter is a polynomial in Z inverse. And FIR digital filter has like three important properties. So the first is it has the finite length impulse response. The second one is they are like always bounded input and bounded output stable. And also they can realize the desired magnitude response and with an exactly linear phase response. The next one is the IIR filter. We will also see how to represent this. That is infinite impulse response with the filter. So this is like recursive in nature, and the transfer function of an IIR digital filter is a rational function in Z inverse. So we will see the basic structure of IIR system. The basic structure is like this. Y of n is equal to summation of ak y of n minus k, where k is equal to 1 to capital N, and then plus summation of bk x of n minus k, and k is equal to 0 to n. So what is our h of z? When we take the z transform and then we find the transfer function, h of z will be y of z by x of z. So it will be equal to coefficient of x z to the power of minus k divided of coefficient of y and z to the power of minus k, here denominator k equal to 1 to n, or numerator k equal to 1 to n. So k equal to 0 to n. Okay, like this is the equation of this impulse, infinite impulse response digital filter. Now we will see like how to represent this. So there is like direct form realization of infinite impulse response digital filter. So we will see that first. The first one is the, and here you can see this is the recursive filter. The current value of output response depends on the previous value. So the digital system structure that is determined directly from either equation is called the direct form one. So in this case, like the system function will be divided into two parts, and that both the parts will be connected in cascade. The first part will contain only the zeros, like the numerator part, followed by the second part will contain the poles. And there will be an intermediate sequence, WM, and so we will see how to represent. So like W will represent the output of the first part and input to the second part. So WL, it is the output of the first part and input to the second part. So what is the output of the first part? That is a summation of k is equal to 0 to m bk x of n minus k. This is our first part, okay? And then y of n is equal to k is equal to 1 to n ak y of n minus k plus w of n. So in this way, you can see that we have used the output of the first part, and then we have found y of n. The possible uh, so the input is given x of n, So this will be our zeros part, that is the first part, that is h1 of z, and what is output here? W of n. Now again we give the pole part, that is h2 of z, and then finally we will get y of z. In the input also we can write x of z and w of z. Okay. So basically w of z will be x of z into dk z to the power of minus k, k is equal to 0 to n. And y of z is equal to ak z to the power of minus k plus w of z. And this can be also written as w of z divided by 1 minus k is equal to 1 to n ak z to the power of minus k. So now we'll take example and we will see the how to represent the direct form 1. So example, develop a direct form 1 realization of the difference equation y of n is equal to b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus b3 x of n minus 3 minus a1 y of n minus 1 minus a2 y of n minus 2 minus a3 y of n minus 3. So we have to represent the direct form 1 realization. So first we take the Z transform. So when we take the Z transform, what we will get? We will get y of z plus a1 z inverse y of z plus a2 z to the power of minus 2 y of z plus a3 z to the power of minus 3 y of z, and this will be equal to b naught x of z plus b1 z inverse x of z plus b2 z to the power of minus 2 x of z plus b3 z to the power of minus 3 x of z. So now we will take y of z common on the left hand side. So we will get 1 plus a1 z inverse plus a2 z to the power of minus 2 plus a3 z to the power of minus 3. That is equal to x of z will take common and we will get b naught plus b1 z inverse plus b2 z to the power of minus 2 plus b3 z to the power of minus 3. Okay. So now your transfer function that is given as h of z, that is equal to y of z divided by x of z. So this will become b naught plus b1 z inverse plus b2 z to the power of minus 2 plus b3 z to the power of minus 3 divided by 1 plus a1 z inverse plus a2 z to the power of minus 2 plus a3 z to the power of minus 3. So this is the transfer function. Now we have to represent it as a direct form 1. So the corresponding direct form 1 So here what we have seen for direct form 1, first we will represent the zeros part and then we will represent the whole part. Okay. So x of z is first. The first multiplier will be d naught plus, now there will be a delay unit z inverse, so that is multiplied with d1. Okay, the second multiplier is d1, so again there will be plus. Now again we have a delay unit, that is z inverse, so this will be multiplied with d2, and again let's do a small correction here. So there will be adding adder here. Now, is there any more delay? Yes, there is a z to the power of minus 3. So, we'll add one more delay unit. Now, this time our multiplier is d3. Okay, so the zeros part we have completed. Now, we have to complete the whole part. So, let's suppose this is our y of z. So, y of z, the first there is delay unit z inverse, and then z inverse is multiplied with a of 1. We cancel over discharge, so we will have a 2-minute break. So the first, like you can see that is 1 plus a1 z inverse. So the first multiplier will be only the 1. So we'll directly send it to the adder. Okay, from the output y of z. So, so here it will be 1. This will be minus a of 1. And the second addition is a of 2. So again we will put the delay unit minus a of 2. Oh, sorry. Here we have to give the order and then now again there is a delay unit and the coefficient is a of 3. So this is the direct form representation of the high filter. Direct form 1. So in direct form 2, what we are going to do is that, like there is, as you can see, there are lots of delay units are there. Like delay units are this side also and this side also. So there is additional complexity and cost because each delay unit will cost us. So now, how we can combine both the delay units? So this is the second part. So this is the direct form 2 representation. So we'll see about direct part 2, direct form 2, and then we will solve some more questions. Let me check once this video is recording or not. So, and this video will be recorded and will be uploaded on the YouTube as well. So there you can also ask questions if you feel any difficulty. So the next is the direct form 2. So like as we are dealing with the linear system, so the order of these parts can be interchanged. So this is the second direct form realization. In direct form 2, the poles of HZ are realized first and the zeros second. So this is the main part. In direct form 2, poles of HZ are realized first and the zeros as second. Okay. When the transfer function Hz is broken, like it is divided into two parts, H1z and H2z. Where H1z has only poles and H2z has only zeros. So Hz will be divided into two parts, H1z and H2z. So our H1z will be only having the poles. So that is 1 minus summation k is equal to 1 to n ak z to the power of minus k and h2z that is equal to summation bk z to the power of minus k and k is equal to 0 to m. Okay. So the decomposition for the direct form 2 realization will be like there will be intermediate sequence wn or w of z. So that will be introduced to obtain the output of the filter. So like first there will be x of z and this one is our pole and then there will be h2 of z and then we will receive y of z. The intermediate unit is w of z, the output of the first unit, that is the pole. Okay, or we can say here x of n. So here our wn, the intermediate unit is summation k is equal to 1 to n ak w of n minus k plus x of n and y of n is equal to summation dk w of n minus k. So now taking the z transform, we will get w of z is equal to x of z divided by 1 minus summation of ak z to the power of minus k and y of z is equal to w of z summation dk z to the power of minus k. Okay. So the direct form 2 realization requires only the larger amount and storage element. So we will see how. So how many storage elements required here? Elements required in direct form 1 is equal to, let's suppose here this there is like our B is going from 0 to K is equal to 0 to M. Okay. And the second one is going from, like there will be M units here and N unit here. So there will be M plus N unit. Okay. So these many numbers of direct like storage elements are required here. But in this, like from the same transfer function, we'll do the representation of direct form 2. Now we'll take one example, then it will be more easy. So let's take one example. Determine the direct form 1 and 2. Like we have to determine the direct form 1 and 2 realization for a third order IIR filter, IIR transfer function. The transfer function is given as h of z is equal to 0.28 z square plus 0.319 z plus 0.04 divided by 0.5 z cube plus 0.3 z square plus 0.17 z minus 0.2. So h of z will be, so what we will do, multiply the transfer function uh, like in numerator and denominator, multiply it by 2z to the power of minus 3. So what we will get after this? We will get 0.56 z inverse plus 0.638 z to the power minus 2 plus 0.08 z to the power of minus 3 divided by 1 plus, to make this work we have multiplied with 2 into z to the power of minus 3. 0.6 z inverse plus 0.34 z to the power of minus 2 minus 0. Again, it will be multiplied with 2. It will become 0.4 z to the power of minus 3. So this is our transfer function. So now we will first see the direct form 1. So in direct form 1, first we'll have x of n, that is the input. Okay. Now the first delay unit, z inverse. So we will realize the zero part. So this is a zero part. So first we have to realize this. So now the first delay unit is multiplied with 0.56. Okay. Again, the second delay unit is multiplied with 0.638. Now there is a third delay unit that is multiplied with 0.08. Okay. So this we have realized the zero part. Now we have to realize the pole part as we have studied the structure of direct form 1. So here we will have y of n. Now the first delay unit have a multiplier of minus 0.6. Now the second delay unit that is a multiplier of 0.34. Okay. And the third one will be plus 0.4. This is a direct form 1 representation of this transfer function. So what we can do, we'll make it a little small so that we can make it again and this we will cut it out. Now what happened? So we will make into the next page. So now this was our direct form 1. Now we will make direct form 2 from this. In direct form 2, the first realization will be the whole part. So x of n is there. So the first delay unit is z inverse. Now to this z inverse, as you can see, minus 0.6 is the multiplier, and then we give it to the adder, and again to the zero side, that is 0.56 is the multiplier. So now we are using only one storage element for both the poles and zeros. Okay. So now again there will be a second delay unit. So in the second delay unit, there will be two multipliers. Okay. So what is those value? 0. Minus 0.34 from the pole side, and for the zero side 0.638. Okay. Now there is one more delay unit, that is having a multiplier of 0.4, and this side 0.08. So this is our direct form 2 representation. So number of storage elements is equal to m plus n. So here it is 3 plus 3 is equal to 6. Here number of storage elements is equal to max of m comma n. So max of 3 comma 3. So that is equal to 3. Okay, whatever is the value maximum m or n. So that is the number of required storage element in this. So this is the direct form 2 representation. Okay, there is another cascade realization, but that will not study today. Now we'll solve some questions based on this. So just give me a minute. To find the number of adders, constant multipliers with gain 0 or 1, that is gain is not 0 or 1, and unit delay buffers required to realize h of z using single flow graph of direct form 2. So in this question, it is a direct form 2 is given. So our h of z is equal to 3 minus z inverse divided by 1 plus 2 z inverse minus z to the power of minus 3. Okay, so first we will realize the pole part. So we will take x of n, and then there is the adder, and again like how we have done here. So there will be this adder is not required at all. Yeah, okay, let it have. So there is one delay unit z inverse, and the pole side, the multiplier is first 2, and again there is a delay unit z inverse, and there is no multiplier here, so again there will be delay unit z inverse, that is z cube. Now again this side the multiplier is 1. Okay, so we have realized the pole part. Now the z inverse have the multiplier as minus 1. Okay, and this is our y of x. So we can directly get, or we can get. So this is the multiplier will be here 3. So as you can see in the numerator there is a 3. So that we forward to do here. So now the total number of multiplier multiplier is 2, 3, minus 1 and 1. So 1 we have to not count. So there is 3 multiplier, and adders. Adders are, so see, this is not required, there we can directly send. So now we will do little correction. Again, here this is not required because this is redundant. So let the consider charge. So, so this is also redundant. So we can directly give this like this. And now again this is also redundant. So how many adders are there? Three adders are there and three delay units and three multipliers. So option C is the correct answer for this question. So understood? Now we'll move on to the next question. So the given signal flow graph, which of the following is the transfer function? So the transfer function h of z can be written as summation m is equal to 0 to m bm z inverse of minus 1 divided by summation, sorry, 1 minus, as we have studied before, the transfer function representation a of l, we can write z of minus, we can write n here, n is equal to 1 to 1. So in this case, so each z inverse like will be the delay unit here. So this is a direct form 1. So this is a 10 z inverse and 15 z to the power of minus 2. And 8 plus, so denominator will be 8 plus 10 z inverse plus 15 z to the power of minus 2. And numerator will be, sorry, this is the numerator. Because we are taking, just a minute, I got a call. So the denominator will be the zeros part, that is 1 minus, and it is a 12. So 12 z inverse. Okay. So our transfer function here will be 8 plus 10 z inverse plus 15 z to the minus 2 divided by 1 minus 12 z inverse. So option A is the correct answer for this question. Okay. Now moving to the question 3. Convert the following signal flow graph of a transfer function so that it can be implemented more economically. So this is the direct form 1. So to convert it more economically, we will do direct form 2. So in direct form 2, we have to check all, like first we will realize the whole part. So here you can see 4, 9, 8, 6 holes and the zeros are 2, 7, 5. So this is the zeros. Okay, and then we are getting y of n. Is there any difference between these two? I think all the options are same. No, no, the arrows are different. So option A is the correct answer, as we can see. So this is the direct form 2 representation of this given question. So option A is the correct answer for this question. Okay, because see here, see this is a delay unit, so this is the arrow direction is wrong in this. Okay, and again here is the arrow direction is wrong here. So option A is the correct answer for this question. Now moving to question C. How many unit delay elements would be needed to realize HZ in direct form 1? So in direct form 1, we have studied we will require M plus N units. Option C. In direct form 2, we will require maximum of N comma N. Okay. Now coming to the question number 6. So for the given signal flow diagram, answer the following question. If y1 of z by xz is of the form 1 plus az inverse 1 plus bz inverse, and if a and b are real numbers with magnitude less than 1, then the values of k1 and k2 are also real and have a magnitude less than 1. So we have to verify whether the statement is true or false. From the given figure, here we can see y2 of z that is equal to xz plus here you can see k1 z inverse x of z. Okay. Now y1 of z that is equal to y2 of z plus k2 k1 z inverse x of z. Okay. Our y1 of z is equal to x of z plus k1 z inverse x of z plus k1 k2 z inverse x of z. So y1 of z is equal to xz plus if you take z inverse common, it will become k1 1 plus k2 z inverse x of z. Okay. Now they will return k2 plus k2 z minus 2 x of z. Z power minus 2 x of z. So plus k2 z power minus 2 x of z. So this is our y1 of z. So now the A part, like the question number 5, here what we can do, y1 of z divided by x1 of z, from this equation, we will get 1 plus k1 1 plus k2 z inverse plus k2 z to the power of minus 2. Let's see whether I have written that correctly or not. Now, and this in the form in the given in the question is 1 plus a z to the power of minus 1 plus b z to the power of minus 1 plus ab z to the power of minus 2. So, k1 1 plus k2. This is equation 1, this is equation 2. So, now equating equation 1 and 2, we will get k1 1 plus k2 is equal to a plus b. Okay? And k2 is equal to ab. So from this we will get k1 is equal to a plus b divided by 1 plus ab and k2 is equal to ab. So if both a and b are real with magnitude less than 1, then k1 and k2, and this will be less than 1, k2 is also less than 1, and this will be like a plus b divided by 1 plus ab. So yes, that will be also less than 1. Let's take a value 0.6 plus 0.4 divided by 1 plus 0.24. This will be equal to 0.1 divided by 1.24. This is also less than 1. So let's put validation. I have taken some two random values. So option A is the correct answer. That is the true. Okay. Now moving to the question number 6. So y1 of z divided by x of z is given as 1 plus 2.5 z inverse plus 0.5 z of minus 2. So now we have to find the values of k1 and k2. So here in this question, we know that y1 by xz is 1 plus az inverse plus 1 plus bz inverse. y1 by z x of z is equal to 1 plus a z inverse into 1 plus b z inverse. So when we do y1 of z by x of z, we will get 1 plus a plus b z inverse plus ab z minus 2. So here ab is equal to 0.5 and a plus b is equal to 2.5. So a is equal to say 1 by 2. So b is equal to 2a. So now when we substitute 3a is equal to 2.5. So we will get a is equal to 2.5 by 3 and b is equal to 5 by 3. And what was the value of k1 and k2? K2 is ab, k1 is a plus b divided by 1 plus ab and k2 is equal to ab. So you can directly get k2 is equal to 0.5 and k1 is equal to a plus b, that is 2.5 divided by 1 plus 0.5. Sorry, we don't have to calculate here these things. The value of a and b, I thought it is required, it's not required. Because directly it is in the form of a plus b or ab. So the value of k1 is equal to 2.5 by 1.5. So that will be 5 by 3, 1.66, and k2 is equal to 0.5. So k1 is equal to 1.67 and k2 is equal to 0.5. So option B is the correct answer. Okay. Also, we will see like some like we have not studied about a fire system. So we'll see the basic structure of a fire system. Just we will see, and then we'll close the lecture today. So this is h of z is equal to summation of h of n z to the power of minus n is equal to 0 to n minus 1. Okay, and here y of n is equal to h of k x of n minus k and n is equal to 0 to n minus 1. So here y and x are the output and input sequence. So we can realize this like this. So this is our x of n minus 1 if this is our x of n. And then again, this is our x of n minus 2. So dot we can realize. So from here, x of 1 with the adder, there it will be x of 0. Okay. There again, it will be h of 2. Okay. Now here it will be h of n minus 2. So lots of storage element in between up to m minus 1. And this will be h of m minus 1. So this is a direct form realization of FIR system. So done. So today we'll end up the lecture here only. We will meet again on the next Monday between at 7 o'clock. So thank you everyone for attending today's lecture. We'll close the lecture here. If you have any doubt, you can ask. And this video will be uploaded on YouTube and the link will be provided in the NPTEL portal. So from there also you can ask anything. If you have any doubt, you can comment down there also. Thank you.